Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Viscous relaxation is a plastic deformation process driven by gravity that tends to smooth out geological features by making hills less prominent and valleys less deep. The process is generally slow, but it can be speeded up by reducing the viscosity of the medium by heat or by vibrations that promote liquefaction. Viscous relaxation has nothing to do with relaxing by the ocean. The glacier ice impact hypothesis published in 2017 proposed that the Carolina Bays were created by secondary impacts of glacier ice ejected by an extraterrestrial impact on the Laurentide ice sheet. Well-preserved Carolina Bays are conic sections that have mathematically precise elliptical geomorphology. This is a clue that the bays originated as inclined conical cavities, also called penetration funnels. The glacier ice impact hypothesis proposes that viscous relaxation decreased the depth of the conical cavities to produce the shallow elliptical features that are found today in Nebraska and in the east coast of the United States. Experiments confirm that oblique impacts on viscous targets create inclined conical cavities that are elliptical when viewed from above. The raised rims around the cavities are characteristic of impacts because impact cratering displaces material laterally by horizontal compressive forces and ejects debris ballistically to create stratigraphically uplifted rims. A high-speed impact on a hard surface goes through several stages. During the contact and compression stage, the projectile contacts the target surface. The swiftly moving projectile pushes target material, compressing it and accelerating it to a large fraction of the impact velocity. Most of the projectile's kinetic energy is transferred to the target, creating a hemispherical shock wave that starts the excavation stage. Target material is displaced, forming an ejecta curtain that covers the terrain surrounding the final crater. During the modification stage, loose debris slides down the steep interior walls of the crater, and the rebound of the target surface may form a central peak. On a much longer timescale, isostatic rebound may eventually flatten the crater. Professor J. Milosh described the viscous degradation of craters in his book about impact cratering. Simple and complex craters are the immediate result of impact crater excavation and collapse. However, long after these rapid events have occurred, craters on most planetary bodies continue to change and degrade toward the ultimate limit of gravitational stability, a level plane. One degradational process that seems to be particularly effective on the icy satellites of Jupiter, but which also may be important for large craters on Earth and other bodies, is the slow, viscous flow of the material surrounding the crater. No material is truly solid. Research on geological behavior of crystalline solids during this century has shown that all substances flow or creep slowly under applied stress, however small that stress may be. Some of the craters in Ganymede show evidence of extensive viscous flow. There are craters that lack a central crater depression and a rim. They are discernible only from the contrasting colors of the surface material. The featureless craters in Ganymede are similar to the ghost Carolina Bays, whose existence can only be discerned from the outlines of their sandy rims on plowed fields without vegetation. The glacier ice impacts that made the Carolina Bays had sufficient energy to liquefy the saturated ground of the east coast. Unlike high-speed impacts, ballistic impacts on viscous targets do not destroy the projectile. The projectile travels through the target medium, forming penetration funnels. This animation shows an oblique impact on a viscous target. The oblique impact produces an inclined conical cavity with raised rims. The pressure at any particular depth surrounding the cavity is the product of the density, the gravitational constant, and depth. Viscous relaxation reduces the depth of the cavity starting from the deepest part, which has the greatest lateral pressure. This sequence of images shows that a penetration funnel on a viscous surface decreases in depth from the bottom up. Since the surrounding pressure is greatest at the bottom of the cavity, the centripetal flow of material restores the stratigraphy as the depth of the cavity is reduced. This sequence of photographs shows an ice projectile that penetrated a red layer in a target surface. Viscous relaxation reduces the depth of the cavity and restores the stratigraphy. This animation shows the reduction in the depth of the cavity. Notice that the ice projectile has a lower density than the target medium and it floats as the cavity fills in. These inclined impact cavities were made by oblique impacts of ice projectiles on a viscous target. In this image, we see that the depth of the cavities has been reduced by viscous relaxation and that the ice projectiles have almost melted. The overturned flaps created by the impact are modified into raised rims. A small piece of ice can still be seen in this image. After the ice melts, there is no evidence of the projectile. This is why the origin of the Carolina bays has been shrouded in mystery. The bays look like they were made by impacts, but no trace of the projectiles has ever been found. The ice projectile melts after viscous relaxation, and only a shallow elliptical cavity with raised rims remains. Lakes are formed when viscous relaxation leaves portion of the impact cavities below the water table, as in the case of Jones Lake State Park. The origin of the Carolina bays has been a topic of contentious debates between proponents of an impact hypothesis and proponents of wind and water mechanisms. The verification of the elliptical geomorphology of the Carolina bays clearly settles the question in favor of the impact origin because wind and water cannot produce elliptical features consistently. Experiments of oblique impacts produce inclined conical cavities that look elliptical when viewed from above, and this provides experimental confirmation that the impact hypothesis explains the mystery of the Carolina bays. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.